Hey everybody. Today we're going to have a look at the wireless WiMAX technology. This is essentially the first 4G technology for cellular data networks. And we're going to look at it from A to Z. We're going to divide our discussion into two basic parts. And first we're going to discuss the messaging that goes on in the WiMAX core network. And then we're going to look at the messaging and the RF details over the air between the mobiles and the base station. There's a lot of parallels between WiMAX and LTE, which is very popular today. And I'm going to point those out as we go when it comes to mind. These are parallels that occur on the RF front and that also occur a little bit in the core network on the core network side as it relates to some details of key generation and whatnot. But primarily the parallels are on the RF side. But we'll touch on those as we go. And my goal today is for you to come away with a solid grasp of really how WiMAX works, from the messaging details to some extent anyway. We're not going to go into extreme detail, to the RF, to OFDMA technology and how that works. And we're going to look at it hands-on. We're going to look at it using the Torrent 7240. As I said, in the first part of our discussion, we're going to look at messaging in the core network. So it helps to have a look at the basic WiMAX network architecture before we go anywhere, before we actually look at the system doing anything. And in WiMAX, just as in pretty much all cellular technologies, we have access services network, and then you have usually one connectivity services network server, if you will, entity. It doesn't have to be just one server. So it's like a big triangle. And the CSN is responsible. Its primary job is authentication, but also has a home agent. So all of the traffic, all of the data from the mobile to the network typically goes through the CSN. There's an asterisk to that, depending on some things that can be done. Data, for example, can be shot in the upward direction off the ASN gateway directly. But anyway, it helps to think of it as a big triangle, and it's important to know that the CSN's there for authentication, also acts as a home agent for the mobile. The ASN gateway, care and feeding of the base stations, if you will, but really more so, it's not just care and feeding. That would be OA&M. This is, in steady state, it's doing the majority of the messaging to the base stations. In fact, it's the only entity that really talks to the base stations directly, other than the mobiles. ASN gateways talk to one another sometimes for certain types of handovers. So it's a complicated message flow. We're not going to go into it today. In fact, we're not going to go into handover flows today. It's something that's worth its own discussion, and we may do a presentation on that separately. Also, we're not going to go into idle mode entry and exit. Probably fold that into the same discussion. So with that said, let's transition then to the hands-on part of the discussion for the core network. Okay, so here we have the Torrent 7240 system running, and we're going to put one mobile on the network and then take it off the network, all in one fell swoop. You know what? Why don't we change that and just put it on the network first, then we'll do, say, a ping, and then we'll take it off the network. So there's this script here called setup, which attaches to some base station. It doesn't matter which. So we're gonna execute that. We're going to make sure that we set up tracing so that we capture stuff going messages in and out of the CSN, so the radius for authentication, home agent. And on the MPS side, we're going to capture R6 and R8 and data plane. Okay, we're intentionally leaving off the over-the-air messaging. So we're going to run the script called setup. And there's a bunch of stuff. So we just got the mobile on the network. There's a bunch of stuff that happened over the air, but we are intentionally not looking at it at the moment. So the first thing that happens is from the core network perspective, of course, a lot happened over the air before this. But from the core network perspective is the base station sends the ASN gateway's pre-attachment request. So that kicks everything off. And in the pre-attachment request, it tells the network something about the mobile identity. In this case, the NAI and MSID. MSID is a very key, identity that's pretty much universally found in the messaging and that goes on between the base station and the ASN gateway. And NAI is quite universal as well, but it's not used as much during steady state, hardly any actually. And so anyway, so this is basically saying, hey, ASN gateway, we would like to attach or activate this particular subscriber. And so the ASN gateway turns around and says, yeah, okay, I've got resources. Yeah, let's go ahead and do it. And it sends back some, just basically an ACK message, really. And then we see pre-attachment ACK. Yes, acknowledges that. Then the first thing that happens from an authentication perspective is that the ASN gateway tells the base station, and in turn this will be told to the mobile, hey, who are you? Saying identity request. And EAP is the extensible authentication protocol. It can do a lot of different, ways of authenticating the mobile, a lot of different types of procedures. Today in this flow, we're looking at the most simple method of authentication, EAP MD5. It's just a really simple one. It's useful for discussion, but it's not used in production networks. Instead, they use EAP TLS and EAP TTLS, which are almost the same exact types of security mechanisms found in HTTPS. But those are beyond our scope for today. The system happens to support them, but again, that would take us a little off track. So the mobile turns around and then tells the base station, hey, I am mobile, and it provides its NAI, mobile 3. Then the base station sends that to the ASN gateway in this EAP transfer, which is a UDP message, by the way. And the ASN gateway then sends a radius access request to the radius server in CSN, saying, hey, we would like to get this mobile on the network. So the CSN, the radius server, it responds back with an access challenge. So here you see first the identity response coming back from the mobile, and then the server, the radius server says, hey, MD5 challenge, who are you? Here's a challenge for you, basically like a random number, and you gotta like authenticate it. You gotta crank some algorithm making me back at an answer that I like. So here we see the MD5 challenge going down to the mobile, and we see the challenge response coming back, and then this goes from the ASN gateway to the CSN, to the radius server there, challenge response. It likes it. So it turns around and says access accept. So this is a pretty key message in the flow, because at this point the mobile is authenticated. Now with eTLS, TTLS, there's a lot more that goes on before we hit that stage. But at that point, the mobile says, okay, you can get on the network. And there's a lot of keying information, a lot of security information that is sent from the CSN to the ASN gateway to give it the necessary keying information. And these same types of happen in LTE, by the way. Sort of a key distribution, element of context setup of initial attach, initial network entry in the WiMAX nomenclature. So LTE attach, WiMAX is just a little different flavor. So okay, so at this point the network has authenticated the user. We may let's browse real quick some of these things that are provided by the CSN. Some master key, master security key, different details for what kinds of flows to set up, and so forth. Again, in our discussion today, the goal is not to know every detail of WiMAX, but to have the big picture, to understand the big picture, and that's what matters. You can read a spec, you can read different bits about different procedures or the details that are in certain messages, and you should be able to sort of illuminate yourself on any of those hazy, dark areas, right? But here we're just trying to get the big picture. So this access accept message goes from the CSN back down to the ASN gateway, and then is, of course, relayed down to the mobile. Mobile's told, hey, yeah, rock and roll, you're on the network. Okay. So the next thing that happens is we have this key change directive, which is the indication at a higher level to the base station that, hey, we've done this authentication phase, and there's security keys that are provided, as obviously you can tell by the name of the message, from the ASN gateway down to the base station. Okay, so let's see what's in here. Okay, this is basically saying authentication was okay. So we get the key change ACK. And then the next thing that happens is MS attachment request. So the first phase was pre-attachment request. We're trying to authenticate and so forth. Now we've been authenticated. So now let's get on here. So it's a pretty plain and basic message. Depending on this is something that was added later in the evolution of the WiMAX specs, and we're not going to cover it today. It's just details, and I believe it's optional actually. It certainly was in earlier days. Pre-attachment ACK, and it was attachment ACK, and so then the next thing that happens is we want to set up the data path between the ASN gateway and the base station. Now, all the messaging is UDP, so in some sense that it's just there's no real path in the sense that it's kind of UDP over a packet data network, but in a logical sense there is, of course, a path. And the path is just basically a pair of connection identifiers that allow us to, on the ASN gateway side, to know if we receive a packet, it belongs to what mobile. On the base station side, if we receive a packet, it belongs to what mobile. Very simple. This is very common in data networking in general, certainly in wireless. And that's the key thing that we're doing here is we're setting up this path. And you know, depending on the implementation of the ASN gateway, implementation of the base station, there's, you know, we got to reserve some bandwidth, blah, blah. You know, those are implementation details of how those nodes are put together. But practically speaking, that's the most important thing is those connection identifiers that are associated with the path. So let's have a look at this path registration request that the ASN gateway sends to the base station. So it says, so I want to create two logical paths or service flows. The names are kind of interchangeable. Okay. So we have an uplink best effort path and a downlink best effort path, and those are obviously paired, and that's typically how paths are set up in pairs. We can set up multiple pairs of paths if we want, but that's really a network operator's, you know, discretion how they want to do that. But BE is your default best effort path. And there's a bunch of details in here about, you know, loss information, you know, related to this path, and you know, the direction which we show here, it's uplink, and data path info, data path ID. Boom, it's ID 31, and these messages are going to happen to flow over GRE. Okay. Now WiMAX supports both GRE and IP, and we don't really care so much. It's basically just IP tunneling, and so the base station, for example, will listen for packets over GRE marked with value 31. Actually, that would be the ASN gateway doing that. Similar concept on the VS side. On the VS side, it would be down here. Actually, we don't see it in this message, right? Interesting, huh? But when we look over here at the message sent to the ASN gateway is being told the data path information for the base station. So it's ID 30. So the VS will be listening on ID 30, GRE key 30, for messages downlink for that particular subscriber. So that should make sense if you have a background in data protocols and certainly wireless data protocols. So that's a key piece of information being exchanged there between these two entities for this mobile. And then we send the ASN gateway, the FA, sends a router advertisement. And that's the first downlink message that goes to the mobile, first downlink data message that goes to the mobile. And it sees that router advertisement and then sends a registration request. This is a mobile IP registration request that the mobile sent up to the base station, and the base station is now sending it on up to the ASN gateway. You'll notice that the GRE key is GRE key 31, right? Just as we expected. And at this point, the registration request then goes, is sent from the FA to the home agent on the CSN. And the home agent then responds and says, okay, you're on the network. And then the ASN gateway says, you know, accounting starts to the radius server. Okay, we're at this point the mobile's on, has service, so let's start ticking the clock right here in terms of accounting. And then the server says, okay, I acknowledge that. And it's sort of in parallel with all this, the registration, the mobile IP registration reply goes back down to the mobile. Now you'll notice the GRE key is GRE key 30, just like we said. Right? Okay, so what's this? We see here a path registration request. So what's going on here? I mean, yeah, I thought we set up the data paths, right? Well, as I mentioned, right, there's we have the option, and the operator has the option of setting up more paths. So here, another pair of service flows was set up for voice, basically, or more real-time services. And same exact flow and handshake that we saw before. The IDs are going to be different, but they're still associated with that mobile, just this particular flow, and therefore a different sort of a different gloss association, right? So this then is the key and major flow in WiMAX. So we just looked at it, and I think you should have a decent understanding of the basics of getting a mobile on the network for WiMAX. Now, next, what I want to do is look at, say, a ping. Yeah, so let's just do like a loop back ping here and see what happens. And so here we see echo request go from the base station up to the ASN gateway, and there are keys 31 and 30. Nothing too interesting. And then I'm going to delete the mobile, take it off the network. And so now we've done the deregistration flow, which the mobile sends the base station a deregistration request. Base station relays it onto the ASN gateway, which sends it to the home agent. This deregistration request was a CMIT, or mobile IP, client mobile IP deregistration request that goes to the HA, and HA says OK. And sort of in parallel here, we do a counting stop to tell the CSN to stop accounting, to stop keeping time for this mobile. Also, packet counts and so forth are sent, and it acknowledges that. So there we have the complete flow on the network, data activity off the network. Really basic in some sense, but that is really what so much of WiMAX is all about. It's a simple initial network entry flow, really, or INE, as it's sometimes called. Okay, so that is a look at core network messaging in WiMAX. So now we're going to shift gears entirely, and we're going to bring into play the over-the-air messaging and RF details. So let's take. It's probably a good time for everyone to take a break, and we'll come back and pause it there, and we'll come back in a few minutes and we'll look at the over-the-air RF details. Okay. So now what we're going to do is we're going to look at the PHY details, or physical layer details for WiMAX. This is also known as the R1 interface. And I think a good way to do it for you guys is to start by going at a higher level and then moving down to the RF level. And so the way we're going to do that is we're simply going to run the same script that we did before to get a network on, get a mobile on the network, and we're going to see how that sort of fits into that initial network attach network entry flow that we saw. And hold on one second. But to do that, we're gonna change our tracing settings. So we're gonna turn on tracing for the R1 layer of the air. We're gonna keep our R6 and data plane tracing like we had it before. We still want tracing on the CSN for the HA and for radius. So now we're gonna go ahead and run that. And what we're going to see is the same flow we saw before, but now with the over-the-air messaging included as well. So this is a completely different picture in a sense, but the same picture in other senses. So before that pre-attachment request ever went out to the ASN gateway, there was some messaging that went on between the mobile and the base station. And the first series of messages has to do with a process that we call ranging, and we'll come back to that when we get to the RF details. But basically, for our purposes right this second, we're going to say the mobile sends this ranging message, and it did, range request message, and it has various bits of information such as the MAC version, the WiMAX and MAC version. And the BS says, okay, yes, you are correctly ranged, whatever that is. We'll talk about it in a little bit. It's saying, okay, I don't want you to change your power. I don't want you to change your frequency offset, or your timing offset should be in here as well, timing adjust. Okay, whatever those are. We'll talk about them some more in a little bit. So then the mobile sends this capabilities request message to the base station, and it says, different things about what sizes, it's SST sizes it supports, and what kind of demodulation it supports. We'll get into those in a little bit. But then once that's been received by the base station, then the base station sends this pre-attachment request message that we saw, and we continue the initial network entry sequence. Down here we see the response message coming back from the BS, which is this capabilities response, basically acknowledging our capabilities. And then we see this PKM response message. And if we look in that, it's the identity request that was sent down here from the SN gateway. And there's the, if we look here, identity response, there it is, identity response over the air to the base station. And then this, of course, is sent up to the ASN gateway, and then up to CSN, and we saw that. And then what's in this message? Well, if we look in that message, we see this MD5 challenge, which is the one that was sent by the radius server. And looking back, the mobile sends this challenge response, see, challenge response, and that is then sent to the ASN gateway up to the radius server. Okay. Now, we saw this exchange here. We see the path registration request starting to happen, right? The first set of paths. Notice here, by the way, PKM response. What's this? This is going to be the EAP success. Okay, you've been authorized to use the network. Now, you may notice that some of these messages are sent in little batches, and that's owing to the framing that's occurring over the air. So we'll talk about that in just a minute. But the mobile then sends this registration request message as prescribed by the 802.16e spec. And what's this one here? And this is keying information and AKID. This one, we've got set up to be hard-coded in this particular flow since we're not using ETLS and TTLS and so forth. And then here we're setting up a data path to the mobile. It's the same exact concept that we talked about up here. mirrored out over the air, and there's service flows associated with this uplink service flow and downlink service flow. It's the same exact concept, same numbering to associate things and so forth. Different numbering scheme, but it's the same exact concept, same exact thing going on. And the mobile responds back with an ACK for that. Basically, there's the registration response from the BS. And here, router advertisement. As I mentioned, this was the first message over the air, and here we see it going over the air. And we see the response message up to the core network. Then we see a registration reply. This is the CMIP registration reply. Then there's our echo request in the up direction, basically like a ping. There it is. You see the kind of clumping together of messages because of the framing structure over the air. And so this was the, it looks like the beginning of the second pair of establishment of the second pair of flows for ERT QoS, right? So anyway, we see the echo request, echo reply, and then this particular script did a deregistration request, and pretty straightforward to understand. I think deregistration request, that was for CMIP, and that made its way up to the ASN gateway, and pan over, there it is, going from the ASN gateway to the HA, and the registration reply all the way back, deregistration reply in this case, all the way back down through the network. Then the mobile says to the BS, okay, I'm out of here. The deregistration request, the BS then releases all the data paths associated with that mobile. ASN gateway stops accounting, and the BS acknowledges that. So that's the complete flow. Now you know that should be relatively straightforward. It's the same flow we had before, but with more stuff between the BS MAC and MS MAC over the air there. And this particular flow you'll find you'll see it directly out of the WiMAX spec for the core network. You can see a very similar flow. So now we're ready to look at the next level, which is the RF details over the air, okay? After having enabled tracing, we're going to look at the RF details for WiMAX, particularly for the moment of downlink. And what you can kind of see there is the frame structure, which I'm going to show you in great. Pardon that, HMS tone, if you did hear it. Okay. So here you see this frame structure for WiMAX in the downlink direction. So what is this frame structure? Okay, in WiMAX, we transmit information from the base station down to the mobiles, and then for a period of time, and then the mobiles have an opportunity to transmit up to the BS for a period of time, and then we repeat downlink to the mobiles, uplink to the base station. Okay, it's a classical, simple time division multiplexing scheme. And in WiMAX, as with LTE, the base station is the master when it comes to transmission over the air. So it dictates when anyone's going to send anything, at what time, and who has the right to send and so forth. And so, as I said, the time is divided up into, in the case of WiMAX, typically 5 millisecond frames, 5 millisecond frames, and usually for more of that half or more of that frame is going to be for information. And every frame has in it this thing called a preamble, and then a frame control header, and then the maps, which tell us where bursts of information are in the frame. But let's step away for a moment and discuss what is actually occurring over the air. And what's happening in WiMAX is that we are transmitting a time domain, wideband time domain signal over the air. It's really just a time domain signal. It's wideband. There's a lot of frequency components in that signal. Typically, there's 10 megahertz worth of frequency components in it. And when we're talking in terms of complex modulation over the air, there's negative and positive frequency components, and it sounds really weird at first, but when you look at the mathematics and when you think about it, it makes it makes sense, and especially it makes sense when you look at Fourier transforms. So when we take a time domain signal, we take some segment of time, and we do a Fourier transform. We do a Fourier transform on it. We get the spectrum of frequencies that we're in it. And we're going to see that in a minute. And much of WiMAX and much of LTE operates in the frequency domain. So we're not really looking at that signal in the time domain most of the time. We're looking at the frequency domain. It makes a lot more sense in the frequency domain. But and what we're looking at here, this frame structure is a higher level look at the frequency domain. And let's have a closer look at this frame structure and discuss its details some more. So this happens to be what we're looking at in WiMAX is FFT 1024, whatever that means, right? We're gonna discuss that in more detail in a minute. But what we're looking at in the vertical direction is subchannels, and a subchannel, I believe off the top of my head, represents 24 subcarriers in the FFT. So this is a very logical view of what's going on over there. We're not seeing the physical, but we will in a minute. And there's a whole bunch of random sort of permutation of these subcarriers that occur before actual transmission over the air, and we should be aware of that. But most things in WiMAX refer to the subcarriers from 0 to 1023, for example, in the logical sense. And then there's this scrambling that happens before we go out over the air. But in each frame, there's a thing called the preamble, and it's a known a pre-hand determined or a priori determined setup of the subcarriers, what their values are across the spectrum. And I think this may be getting a little bit confusing without looking at the actual symbol. So first let me define what a symbol is, and then we'll go look at a symbol, okay? And that's going to help you understand what we were talking about. Each one of these slices vertically is a symbol. Symbol 0, symbol 1, symbol 2, and so forth. And each block of information, in this case the SCH, this happens to span 2 symbols. And in fact, in the downlink and WiMAX, typically that's the least, that's the most granular you can get, is a pair of symbols. And so symbols, so there's in WiMAX, the typical setup, there's going to be 1 preamble and then 28 symbols of data. And sometimes it's not modulated, as you see here, the blank area.
And then uplink, we have like 18 symbols of data, and then another preamble. And the most important thing about the preamble is it's repetitive, and that's very useful for a number of different things, not the least of which is it allows the mobile to find a repetitive pattern and synchronize to it. And that's a key thing. So when a mobile is trying to connect to a WiMAX base station, it's looking for that preamble. And and basically there's different ways. There's different ways to figure out, oh, this is a preamble, and it's this particular preamble out of say the 100 different preambles that are defined. It's actually more. So that's one of the main things the mobile has to do in initial synchronization is find that preamble pattern and determine which of a known set of patterns it is. That's the key thing in doing initial synchronization. And we call that the preamble ID. And based on the preamble ID, a lot of things related to scrambling of subcarriers and different things are done. So that preamble ID is really important. So now, let's look not at the frames so much, but let's look at the details of the symbols that are in this frame. So if I go over here to frame, we see this gives us a lot more information. We see the actual RF view of each of the symbols. So, and in fact, I really should have had that up earlier as we started to talk about frames. I apologize for that. But what we see here is this is the preamble. Here's the preamble in its actual real, it's the real view of the preamble in the frequency domain. So here is the preamble in the logical, in the logical sort of domain. And here is in the frequency domain where frequencies go across your screen. Here you don't see the frequencies called out as negative, but they really are. Everything, zeros in the center, and then we have positive frequencies to the right and negative frequencies to the left. And you notice that in the preamble, all of the red subcarriers, we've marked in red, are modulated, but the other ones are not. So it's like modulated, skip, modulated. And that's the way it's all the way across the spectrum. And so you see two different shades of yellow, and those are the unmodulated subcarriers. And that's just the way the preamble is defined to be. And so our mobile side has found that, and we're displaying it here in the frequency domain. Now, we look at the first symbol and the second symbol. Remember I said they were in pairs, and we'll look at that in a second. But this SCH message, whatever that is, was sent over the first two symbols. Symbol 1, you see here, and you see all this green stuff. Those are modulated data subcarriers. And these pink and red ones, you can barely see them, but pink and red, those are the pilots or reference frequencies or reference tones. And pilots are very important for all WiMAX and in fact LTE communication over the air. They're awesome to have from a design perspective because without them, depending on what you're doing, it's impossible to do anything. But they're vastly important in being able to decipher the information that you're doing. And you see that the pilots tell us, where they're basically, as a way to think of them as are references, and in relation to the pilot and where they are, we can determine what the data value being sent within a time or frequency is. That may be a little confusing, and clarify that in a minute. But so we see these pilots here, and we see the data sensors. Now, if we pan down a little bit, you're going to see a different view. This is a constellation diagram where symbol 1 looked at it in a different way. So we're taking, you see the pilots there, pink and red, being displayed at their positions, and by positioning those where they need to be on the x-axis there, the green dots, or constellation points, get positioned where they're supposed to be, and consequently we can sort of read out the data that is behind this symbol. So reviewing just a little bit on what just happened. So we had a whole bunch of green subcarriers throughout the frequency spectrum. We're looking at it in the frequency domain. And each one of those have, we're looking at the amplitude, right? The amplitude at a particular frequency. And if we zoomed in really closely, you would see one dot for each frequency. There's 124 dots, 1,024 dots across that spectrum. Each particular dot, you're looking at the amplitude, actually has a complex component and a real component. So on a Cartesian coordinate plane, if we graph those, we would see this, and that's what we see. So we have an imaginary axis and a real axis. And each dot, depending on which coordinate, which quadrant it falls into, or what we call quadrature modulation, quadrature phase shift modulation, rusty. But there's also what we call 4 QAM and then 16 QAM and 64 QAM, which is exactly the same thing. That's quadrature amplitude modulation, but it's really the same thing. But instead of 4 dots, we have 16 and 64. Okay. And moving to the symbol 2, we see the pilots intentionally in a different color, but it's the same deal. The pilots shift around for the second symbol, and then they're going to shift back to the first symbol. And there are the constellation points for symbol 2, and similar to symbol 3, we see constellation points as well. Now, we should see constellation points. Okay. So if we look, let's see, one second. The FCH, which happens to appear in the first 2 symbols, and it's always defined to appear there because it's called the frame control header, and it tells us most everything else we need to know about the rest of the frame, really it and the downlink map. And the symbol 1 covers the frame control header, but it also covers the maps, the downlink and uplink map. It depends on how we're configured. Sometimes the uplink map immediately follows the downlink map. Sometimes it appears as a separate data burst. And that's kind of a somewhat irrelevant configuration detail. And when they occur together, we call them compressed maps. And when they don't, uncompressed map. So, we're looking at symbol 1 here, but we've got part of the FCH and part of the downlink map in it. And the rest of the FCH and the rest of the downlink map are in symbol 2. I hope that makes sense. So logically speaking, the FCH would appear in these first subcarriers here and these first subcarriers down here. That's logically speaking. But in actuality, what happens is that it's spread randomly across the spectrum because the way carriers are permuted, just randomized and shuffled. And they've got different names for these different permutation schemes. The most simple one is partial permutation of subcarriers of PHY. That is the default. That's typically what everyone uses. So it doesn't matter really. What we need to know is that they're shuffled up. And it's difficult to ascertain really from reading the specs just how the shuffling is supposed to be done. It's pretty involved. But they're shuffled in a way that everyone agrees on, and that gives you some nice characteristics over the air in terms of spreading energy around and so forth. And that's one might argue maybe some security features, but the main thing is spreading the power around the spectrum. So continuing then, if we look at say burst 2 and burst 3, where actual data is being sent to one up into MAC, they can be arranged arbitrarily by the base station however it likes. It's just like allocating memory in a way, and the base station allocates a rectangular block and puts data in it. And this data, the ways that the data is encoded at the MAC layer, it's a little bit beyond what we want to talk about today, but it uses kind of classical error encoding techniques, forward error correcting codes. There's two different types, what we call convolutional codes and circular turbo codes. These are very, very popular, used heavily in the industry. And they're just a little beyond our range of discussion today. So anyway, these bursts are if you look at them at this level, we can see the geometry of the burst. But what are the actual constellation points? Well, if we pan down here, we can look at the system showing those constellation bursts. Like burst 2, here we're just looking at the data points that are associated with burst 2. Like remember before we looked at symbol 1 and symbol 2, and part of that was the SDH, part of that was the maps, right? So here we're just looking at one of the bursts, and we can see all the data points in it.